Hi, my name is James, and I'm here with my teammates Ashi and Supankar, and we're going to present our final project for CS5800 titled Running Maps. First, I'll begin with our introduction and context. Regular physical activity, such as running, offers many significant health benefits. Exploring the city by walking, running, or cycling is a good way to get some exercise and fresh air at the same time as seeing the sights. However, when you're new to a place, it can be daunting to find interesting routes to explore in the city. What if we had software that could generate interesting routes for us? Motivation for this project. Running is one of my hobbies, and I like to choose a variety of different routes to explore an area. I am new to the city of Boston, and I really enjoy running here because of how dense the city is. I can cover a large portion of the city in just a few miles and see many famous sites like the Charles River Esplanade and the Boston Public Garden, but I find it hard to plan new routes because I don't know the city well. This program would make it easy for me to try new routes and see new points of interest.
Hello everyone, this is Shubhankar and this is my motivation. I like visiting new places and exploring new areas and would prefer walking around if I am new to the place. I plan to cover certain historical or other interesting places, but most of us don't know the place and they also want to come back to the starting location. Hence, this motivated us to work on a software which will plan out the route for me based on my interest and then come back to the starting location at the end of the trip.
Hi, I am Ashish Rimal, and this is a presentation for a final project for the course CS5800 Algorithms. We all teammates are new to Boston and love to hang out and explore new cool places here. We also love to run around and keep ourselves fit. So we combined these two ideas that we loved and initiated this project. This project is close to me and has a personal relevance as I really love running around the city, especially during summers. So sightseeing motivates me to go beyond my current running threshold. And at the end, I feel extremely refreshed. And it's like an escape from my mundane routine.
Here is our problem statement. Problem. Given a starting location and a desired mileage, what walking, running, or biking route can be made in Boston that is a loop and passes by the largest number of interesting locations?
Let's take a look into the solution of the problem. To address the problem, we have divided the solution into various parts for better understandability. Let's first take a look of the graph structure. Since all three of us are new in Boston, we wanted to work on Boston map. We delineated various points of interest and also running routes on the actual map. This helped us to translate the map of Boston to a graph. The intersection of roads are represented as nodes. The connection between the nodes are edges. The weight of the edges are distance between the intersections. You can see the nodes and edges in the image. Now, moving on to the program structure. We have node class, which has index, latitude, longitude, and point of interest of a node. The graph class contains the information about the adjacency list, which is a hash map of start index and hash map of end indices and distance. The route planner class, which plans the route, it takes graph object and contains a function called go, which takes the start index, total distance, and the mode. Function go then internally called plan BFS or plan DFS function according to the mode which is being inputted by the user. The two function returns a list of graph for all possible paths that can have a loop. Now, let us take a look inside the DFS algorithm. In DFS, first we mark the current node as visited, add the current node to the current path, check if the current node is the starting node and the desired distance has been reached. Check if the path has not already been created in the list of path. We do that by reverting the current path and checking with each already created path in the list of paths. Add the current path to the list of paths. Delete the current node from the current path for backtracking, then return. For all the nodes adjacent to the current node, initialize new distance to current distance plus distance to the adjacent node. If the adjacent node is not visited, then we check new distance is less than the desired distance or not. Or the adjacent node is the starting node and the desired distance has been reached or not. If true, recursively call DFS util function with adjacent node index as current node index and the new distance as the current distance. Delete the current node from the current path for backtracking and mark the current node as not visited for backtracking. Return the list of paths.
Now I will talk about the other algorithm that we use for generating routes, breadth first search, or BFS. In BFS, we utilize a queue to process nodes and their children. So we create a queue and add the starting node with a distance of 0. Then we loop over while the queue is not empty and pop the top item from the queue, which is the current path. It contains a distance value and a list of nodes which indicate the current path. We check if the current node is a starting node and the desired distance has been reached. If that is true, we check if the path that has been created is not already in our list of valid paths. If it's not in the list, then we add that current path to the list of paths. Then, for all of the nodes that are adjacent to the current node, we calculate a new distance and a new path, including that adjacent node. If the adjacent node is not visited and the new distance is less than the desired distance, or if the adjacent node is a starting node and the desired distance has been reached, we add that new path to the queue. Once the while loop is finished and all nodes have been processed, we return the completed list of paths. Now I'll talk about our time and space complexity. The time complexity of our route planning algorithm is O of k to the nth power. K is the maximum number of edges that any node in the graph is connected to, and n is the number of nodes in the graph. The space complexity is O of n due to the length of the queue holding the nodes in the graph or the depth of the stack, the recursive stack when we're using depth first search. Like I said before, this is an exponential time algorithm, and given the values for our Boston graph, k equals 5 and n equals 84, k to the nth power equals 5.17 times 10 to the 58th power, which is a huge number. Even though this algorithm takes exponential time, we are still able to create routes that are approximately less than 5 miles, which means that our program is still useful.
Now I will talk about similar problems that we studied in this course. The two problems are the Hamiltonian cycles and the traveling salesman problem. As we know, a Hamiltonian path is a set of edges that visits all the vertices such that no one edge is being traversed twice. Similarly, the traveling salesman problem is a variation of the Hamilton cycle, but the edges in the graph are weighted and the cycle with the minimum weight is chosen. To solve the problem in polynomial time, we consider the two approximation algorithm. But here our graph is the representation of the city of Boston, and not all vertices are connected with each other, which is required. And hence the two approximation algorithm will not work in our case unless the desired distance is so long that we don't want to visit every node in the graph.
Let's take a look at some of our example routes that are being generated by the algorithm. This is a route starting from the intersection of Boylston and Berkeley, starting from 0.5 miles to 3.5 miles. This is a route of 3.5 miles starting at Cambridge and Burden. This is a 3.5 mile route starting at Huntington and Ruggles. This is a 3.5 mile route starting at Harrison and Massachusetts. Another 3.5 mile route starting at Commonwealth and Massachusetts. This is a 4.5 mile route starting at Commercial and Foster. Thank you.
Hi, this is a demo to show how the user would interact with our project. Currently, we take input from the command line while running the main.py file, which you can see here. When we run this file, it will ask the user 3 questions and take input from the command line. The first question is, what is the index of the starting position that you want to plan the route from? We can refer to our annotated map of Boston to get this information. For this first example, I'm going to enter index 0, which references starting at Northeastern University near Corey College. The next question is to enter the desired loop distance in miles. For this example, I'm going to use 2.5 miles. The final question is, do you want to use depth first search or breadth first search for calculating the routes? For this first example, I'm going to use depth first search. Okay, so once the user enters all their information, the program generates all possible routes that fit the desired mileage. To check if the route is within the correct mileage, it uses a check tolerance function, which basically checks if the route is within half a mile of the total desired distance or 10% of the total desired distance, whichever is smaller. So we can see this is the route that we've generated, starting at Northeastern University down here and going around the fens and coming back on Massachusetts Avenue. Also, after the map is closed, it outputs all of the points of interest that you will see along your route. Now, so for that first example, we used depth first search. Now I will re-enter the same information, but instead we will use breadth first search to show that we get the same results. So as you can see here, we get the same route. To plot the routes on our map, we use the geoplotlib Python package, which uses map data from the OpenStreetMap project. Okay, now that we have shown a basic route, I will show a couple others just to kind of see the various places that we have around Boston. So node 78 corresponds to starting in the north end of Boston, which you can see right up here, and it goes all around downtown Boston, Commons and Public Gardens, and then comes back through Beacon Hill. I'll show a few others. So index 23 corresponds to the corner of Massachusetts Avenue and Harrison. We will do a 2.5 mile loop, and this time we'll use breadth first search. Sometimes the map does not render all of the edges, but that can simply be fixed by zooming in or out. And we can see the route starting from this position down here. Okay. I'll keep going and show starting from the position of Massachusetts Ave and Commonwealth. So again, I'll do 2.5 miles, and this time I'll use depth first search. Again, we have a slight rendering issue, but that can easily be fixed by zooming in or out. And finally, I'm going to show one last one starting from node index 47, which is right by Boston Public Garden. I do a 2 mile loop and use breadth first search. You may have noticed that in this demo, I made loops that were relatively small in distance. That is because our algorithm does run in exponential time. So just to make it run quickly and make this video look nice, I chose short distances. And that concludes our demo. Thank you very much.
To conclude, we are able to successfully translate the map of Boston City and convert it to graph so that we can plan routes from the given starting point with the help of BFS and DFS algorithms. Currently, the runtime complexity of the algorithm is k times n, where k is max number of edges that any node in the graph is connected to, and n is number of nodes.
Now we talk about the limitations of our project. The runtime of our project is currently exponential due to the type of the problem statement based on the number of nodes in the graph and the number of edges each node has. So the use of this algorithm is limited to small graphs with less dense vertices or larger graphs if we restrict the size of our loop to be less than 5 miles. Boston is a relatively small city, so we were able to generate routes that cover a larger portion of the city even with this constraint. We do not have a front end yet to display our data visually, so right now we are using our console to print the points of interest. Now we talk about the future scope of our project. So in future, we wish to improve the runtime of our algorithm for better performance, that it can be used in more dense graphs. We wish to add more constraints while selecting the routes. So based on users' preferences like inclination, availability of biking lanes. And we also wish to add features such as saving the previous route. So the user is suggested a new route. And we will add a front end to our code for visuals and user interaction. And this is a prototype. Thank you.